Okay, hi everyone. So my name's Stephen. I've been a postdoc here at Imperial for about 5 years now. And I thought I'd talk to you today a little bit about some of the kind of overall stuff that we've been doing here at the AMCG upstairs on radiation transport. So there's been a bunch of people involved in this work over the last kind of 10 years-ish. Here's some of the names, including Richard and Paul, some of our external collaborators. So the title of this talk is a touch misleading. I'm not just talking about preconditioners. But if you've never seen it before, radiation transport is governed by the Boltzmann transport equation, which is a bit of a nasty PDE. We've seen some people actually already talk about it yesterday. So if you've ever done transport of particles like neutrons, photons, radiative transfer, spectral wave modeling, movement of things like charged particles, then at some point you'll end up with a Boltzmann transport equation. So some of the peculiar things about it are it's big. It has a 7-dimensional phase space. Excuse me, I drank too much last night. Try and be super perky, right? So yeah, there's a 7-dimensional phase space. So there's 3 spatial dimensions, 2 angular dimensions that tell you which direction your particles are moving in, an energy/frequency dimension that tell you how quick your particles are moving or the frequency they're in for photons, and there's a time dimension. So it's a linear PDE, thank goodness, at least as I've written it here. And the 2 points here is we've got a nasty-looking advection operator here, and we've got this weird, horrible, dense integral term that tells us how things scatter in angle. So we've got material properties here that tell you how much these particles are absorbed and scattered by the medium that they're going through. And we've got some other sources here. So things like, well, a linear version of that source is things like fission, black body radiation if you're doing photons, things like that. So particles, if you don't touch them and they're moving through a vacuum, they just go in the direction they started in, which makes sense. But if they're moving through a material that's not a vacuum, they can change direction, which is the scattering here when they hit something. And as they do that, they can go up and down in energy or frequency. So I said the phase space was big. That's true. Unfortunately, it's also big in that we need lots of resolution in all of our different dimensions. So if you're doing things like simulating the distribution of neutrons in a nuclear reactor, if you've never seen a nuclear reactor before, there's lots of scales in them. So you start with little fuel pins that are of order a couple of millimeters with a couple of millimeter coatings. You jam a few of those together, and by a few I mean a couple of hundred, in these big sort of assembly things. And then you start gluing them together to make a big reactor. So geometry resolving meshes for those sorts of things need billions to trillions of spatial elements. Similarly, in angle, so to capture directions, there are problems where you need lots and lots of resolution in angle. So things like particle accelerators, where you've got kind of a centimeter tube that goes for 100 meters, has a really, really small solid angle down it. This is an example of a little particle accelerator in Russia, and some nasty things here include it's got some bends in it, which means you can't just do nice things like, well, I can see the end of it, send things that way. So a good example of resolution in angle that I like to steal is the moon from Earth. If you look up in the sky, right, the moon has a solid angle of about 10 to the minus 5 in the sky. Pluto from Earth is like 8 orders of magnitude worse, something like 10 to the minus 13. And these can be kind of, I don't want to say realistic radiation transport problems, but surprisingly you need really stupid amounts of resolution to resolve some problems in angle. Similarly, in our energy/frequency dimension, this is what the one of the material properties looks like for uranium-238. So this is the energy of the particles, and here is how much they, I think this is the absorption cross-section. Yeah, captured, so the green one. That's not a nice, easy, smooth function, right? So you need lots of resolution to capture that in energy. Of course, you can homogenize in all your dimensions, but I just kind of wanted to show you that, yeah, these 7-dimensional problems need just stupid amounts of resolution. Worse than that, the linear systems that pop out, because we have advection operators, they're not SPD, they're not symmetric. Currently, people tend to solve 10 trillion degrees of freedom sized linear systems in these problems, even a little bit bigger now. Because of those integral operators for scatter that tell you, well, I was going this direction, I've changed direction, you get big dense blocks and angles sometimes. So you've got big dense blocks living on kind of a spatial finite element stencil, and then those are blocks living in an energy stencil. So these linear systems are big and hard. Even worse than that, in regions where your material properties go to zero, so for example, a vacuum, you have pure hyperbolic behavior. Regions where you've got lots and lots of scatter, they tend to go parabolic, and those happen in space and angle. So your material properties depend on lots of your phase space variables. So we don't just tend to solve problems that are hyperbolic or parabolic. Problems have different regions where they're both, which is nasty. So given all these things, in particular how big these systems are, you have to be matrix-free. And not just global matrix-free, but you can't store basically any of your spatial tables in space, angle, or energy for the most part, depending on what you're doing to discretize your angular domain. That obviously restricts the choice of things that we can do in terms of solvers and discretizations. Furthermore, when I say low memory, I don't just mean matrix-free. Common solvers that for these sorts of problems store less than a single copy of the solution. That's how low memory we're talking. And of course, because we're crazy, we want to couple all this to multiphysics. Fluids, heat, stress, etc., etc. So there's not particularly many discretization solver parallel technologies that kind of glue together to give you something that works given all those constraints. They're very tightly linked, all the pieces in this puzzle. So if you've ever done any radiation transport, you might have seen things like, really the only thing that works and scales is doing DG finite element in space, doing a collocation scheme in angle, or a P0 finite element / finite volume. Because if you can do that, then you've got a series of discrete directions in angle. And if you've got a structured spatial grid, you can essentially do an ordered, very specially ordered Gauss-Seidel to invert your streaming operator. So that's the one that does all the transport. And then you can map to a kind of diffusion type problem to pick up your scattering. And they all work very nice and well and scale out to like hundreds of thousands of cores on kind of the biggest machines you've got and can think of. But there are some problems with that, and one of them is that special structured ordering for your Gauss-Seidel. They tend to be called sweeps in kind of transport lingo. Doing that on an unstructured grid, so determining the order in which you have to do your Gauss-Seidel for an unstructured spatial mesh, ends up being an NP, I want to say hard or complete, I always muck up which, scheduling problem. So they don't tend to scale very well in parallel as well, because you've kind of lost the structured deterministic, I shouldn't say deterministic, you've lost the structure in your sparsity that gives you predictable parallelism. Furthermore, what if you want to do different things in angle? What if you want to do perhaps adaptivity in angle? Or try out different angular discretizations? The fact that we're tied to, for the most part, these very structured Gauss-Seidels means we don't get to play around with these things scalably very much. And if you start pulling on a thread, this is all a big house of cards. You start pulling at the solver, your angular discretizations, all these things kind of tumble down, you've got to start from scratch. So that's some of the things we've been working on the last kind of 10 years here in a code we call Fetch2. So we do unstructured spatial finite element for these problems, and one of our things is we want to try and avoid sweeps as much as we can. So we built space angle matrix-free multigrids in PETSI for these problems. So there's a lot of mat shells involved, which means, of course, writing essentially all of our own kernels. So we do some peculiar things in angle for radiation transport. So we do P0 DG like everybody else. We also use spherical harmonics methods, which are a series of high-order polynomials on the sphere. So if your problem's smooth, you get nice convergence. We do filtered versions of them. And we also do a bunch of different wavelets in angle for various reasons. So we have regular and goal-based adaptivity in both space, angle, and I won't say energy, but energy, which is nice. And that's adaptivity in both space and angle. And more importantly, a couple of our different discretizations can adapt in angle energy. Did I say that already? I did. Yeah. Good. And we get okay parallelism from some of these problems, scaling up to about 30,000 cores, which is pretty decent for an unstructured radiation transport solver. So I'm going to talk a little bit about the matrix-free multigrid here. So of course we need the sort of standard building blocks for a multigrid. A smoother, we don't want to use a sweep because we know they won't scale. Means we have to use pointwise or matrix-free smoothers. Oh, I've mucked up my reveals there. Of course, if we're using pointwise or matrix-free smoothers, we've got some constraints. You might think, well, use things like polynomial smoothers. Eigenvalue estimates are hard in these problems. Your eigenvalue estimates don't converge particularly well. So what do we end up doing? Well, we're going to go a bit ham for the moment and do a Jacobi preconditioned GMRes in each of our multigrid steps for our smoother. And one of the things I should point out here is you might go, oh, well, that's a trivial smoother. For these problems, given some of our constraints, our matrix-free, and the fact we've got our weird angular discretizations, sometimes even building diagonals in these problems is really hard, particularly given our big, dense blocks in angle. So what are we going to do to restrict and prolong? Well, we'll just inject in our course nodes, and let's just do some averaging to start. Just average your fine nodes based on how they're connected spatially. So our course matrices, we can't, of course, just do a matrix triple product because we don't have our matrix. What can we do? Well, we can glue together our spatial elements in the classical kind of element agglomeration multigrid type of way. And then we can build coarse spatial tables. And then do matrix-free mapvex on our coarse grid. Because, of course, we want all of our levels of our multigrid to be matrix-free. So, of course, you might say, well, this looks like a terrible multigrid for an advection type problem. And you're right. The good news is, though, it's not as bad as you might think. So here's a typical benchmark problem for radiation transport called the C5G7 problem. So it's got a few different materials here. It's a kind of low-resolution, homogenized version of a reactor. We've got a bunch of different materials here and some little fuel pins that do fission, some moderator here. And the interesting thing about this benchmark is that there are 7 different energy groups here. So you've got neutrons that are really, really quick, and they tend to just fly through things. They don't scatter very much, so you get hyperbolic type behavior. And then the low energy groups, you get very diffuse behavior. So it's a nice little test for a multigrid. But I thought I'd show you some of the element agglomeration stuff. So if you start with an unstructured spatial grid, there's about 8 or 9 algorithms you can think of in the literature that glue elements together in a way you might find nice. You can see there we've started gluing them together in a fashion. And you can do all sorts of things like restrict your agglomeration to different materials and things like that, like we've done here. Coarsen again. Coarsen again. And of course, one of the odd things about the spatial grids on your lower levels here is they don't tend to look like normal finite elements, but you can still treat them like they are, given you've projected down the coarse spatial tables. So yeah, you end up with odd-looking faces and odd numbers of nodes on your lower spatial multigrid levels. So I thought I'd show you, again, this is just a very high-level talk, so I'm not going to talk too much about results in these problems, but here's a nice example of convergence for this problem where these are our hyperbolic type groups, these are our diffusive type groups, and you can see, obviously, we're using a multigrid. It's a multigrid that's built using the normal kind of elliptic ingredients. You would expect it to do well for a diffusion problem. It does. The nice news is it doesn't do too badly for a pretty hyperbolic problem, which is nice. And those lines are nice and flat, which is what we want to see. So if I've convinced you with one slide that our multigrid works, no, I haven't, we can move on and talk about some of our adaptivity in angle, because that's something that we've really been working on, or I've been working on the last kind of year, is trying to build scalable angular adaptivity. Because there are problems, again, like the Jupiter or Pluto in the sky, that you need just absurd degrees, you need absurd resolution to capture. And you have to do H adaptivity. You can't do anything like P. You need to be using low-order basis functions to get there, because you've got such horrible discontinuities in space and angle. So all you've got is H adaptivity, really. And we've built structured H adaptivity on the sphere with some Haar wavelets, which are nice. And they have the properties that they just look like structured quad trees when you adapt. And most importantly, you can map between a wavelet space and your original P0 face with a fast wavelet transform in order n time, which is nice. A minute or two? Yeah. Oh, goodness. Okay. Well, yeah. Here's some nice adapted spheres from some problems, and you can see maybe that we've applied different resolution in different parts of the problem where we need it. The thing that a wavelet gives you is the ability to do that by thresholding, if you've ever used wavelets, so you've got a nice error metric for free. They converge scalably. We can do some parallel stuff. Here's an angular multigrid scaling, strong scaling to about 12,000 cores. A bit of a small problem. There's only about 1 billion degrees of freedom. And we can weak scale okay for hyperbolic type problems. We can do spatial adapts, we can do angular adapts and load balance in parallel. And we've been playing with a bunch of things like L1 Jacobi smoothing, some weird GM resers, and most importantly, thinking about the new kind of asymmetric multigrids for our operators when they're hyperbolic. And some multiphysics, some coupled fluid adaptive radiation transport. These were for radiative transfer for photons. So I guess I should stop there. Thanks.
Do we have a quick question here, Matt? Okay, so yeah, that kind of multigrid convergence for the hyperbolic is pretty amazing, just to me.
Yeah.
My question concerns, like usually the just so story that I understand is that if I take a discretization of the hyperbolic equation and then forcing it, I change the dispersion equation, so it looks different from the Boltzmann velocity is different from the Bohr approximator of the finder. So you don't see this? Do you see the crest in the right place when you get the force defined? Why does that happen in this equation?
Yeah, so we've got a weird spatial discretization. So it's a CG plus a DG, essentially, where we do a static condensation on the DG bits. And we use an approximation for, it's Schur complemented together, and we use an approximation for our DG part to make it scalable, because it's, bigger and more coupled than the CG version, essentially. So those DG bits also get projected down onto the lower grids as well. So what you get is essentially combined stabilization from all of the elements that you've glued together.
Okay, can you interpret that as the wave speed looks the same on both somehow?
So, yeah, don't know.
Okay, maybe we can talk about it at lunch.
Yeah.